example 6, and this one states, find a vector that represents the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals to 2. So this is a line, there's no square. This one is just a circle, and then the z is just infinite, just up and down. And basically you get a cylinder. So here I've graphed it out. Here's the solution. So solution, the figure below shows how the plane and the cylinder intersect. So I'm going to go to GeoGebra right here. All right, so here's GeoGebra, and there's a cylinder, there's the plane, and then there's the intersection right there. So we want to find this points of intersection there. So basically find a vector function that represents all the points where this intersects the plane and this cylinder. All right, so let's get back into here. So here's how it looks like, and so on. All right, so the figure below shows the curve of intersection C, which is an ellipse, and you can see this is an ellipse right here. A circle would be a perfectly perpendicular to this. There's a horizontal plane cutting it through, but it's at an angle, so it's going to be an ellipse. And before I graph it, I'm going to find out all the points of intersection, or just several points. I'm going to find 4 points. And yeah, 4 points for just specific numbers that are easy to calculate. So what we have is we have the cylinder x squared plus y squared. I'll erase this. X squared plus y squared. This equals to 1. All right, and then we also have the plane y plus z equals to 2, like this. All right, so let's just double check that. Yeah, so we have x squared plus y squared equals 1 and y plus z equals to 2. All right, so what we could do here is I'm just going to rearrange this y to make it equal to 2 minus z. So this one is just equal to y. Move the z over to the other side, 2 minus z. And then we could throw this inside. Yeah, so we could throw this inside there, and then we get basically the point of intersection. So we put the y inside there, replace it, and this is at the intersection. I'll put at intersection. At intersection. So at intersection, we're going to have the equation where these all have to match. So we're going to have x squared plus y. Well, y, if it's at the intersection, it needs to fit both equations. So we plug that y is going to equal to 2 minus z squared plus 1, like that. And whoops, not plus 1. This equals to 1. All right, so we have this. And now let's find a few points. So at so I'll move this arrow like here. So at an easy one, this would be at x equals to 0. So that just vanishes. At x equals to 0. What we end up having is, well, we're going to have a 0 is x squared plus 2 minus z squared equals to 1. In other words, now we could take a square root. So square root is just going to be, well, 2 minus z squared both sides equals to plus or minus square root 1. And that just equals to, well, because again, you can have a plus or minus, yeah, minus 1 times minus 1, it also gets equals to 1. So, and if we go further, this just equals to plus or minus 1. Now I'll just write that down for completeness. So this equals to plus or minus 1. So in other words, what we get is, well, z, move this over to the other side, and then move this over to this other side. We're going to have z is equal to, well, 2. And then instead of plus minus, we get minus plus. Again, it doesn't matter. minus plus 1. I just do it for completeness, just keep track of the direction of the arrows. But it doesn't matter because this is either or. So then, in other words, z is equal to 2 minus 1 is 1. Or 2 plus 1 is 3. So z is equal to 1 or 3. All right, so we have that, and then we could plug that into y. So then this means that y is equal to, well, 2 minus z, which equals to 2 minus 1. I'll just do it like this. Equals 2, yeah, like this. Like that. Yeah, just fix that up. So make it like that, equals to, well, 2 minus 1 or 2 minus 3. So this equals to 1, or we can have it as negative 1. All right, so thus this means we have, well, 2 points of intersection. Thus, 2 points of intersection for this case. So we have at x is 0. So at x is 0, we're going to have z is equal to 1, and if z is equals to 1, y is equal to 1, like that. Or and then x is 0, and then if z is equal to 3, put a blank, we'll go 3, then y is equal to -1, like that. So we have 2 points there. And going further, so likewise, for x is equal to another, let's just pick another number, plus or minus 1. And here, the reason I put plus or minus 1 is because right here, we could put a plus 1 squared or minus 1 is still going to be 1, and it's a simple one to evaluate. So then what we end up having is, we're going to have, well, plus or minus 1 squared plus, this right here is at the intersection, 2 minus z squared equals to 1. Like that. So same thing as before. Now this one, plus or minus squared, is just always going to be equal to 1. Equals to 1. And move this over to the other side. This cancels, so what we end up having is, well, a 2 minus z squared. Again, I'll just put it for completeness, 1 minus 1, or I'll just cancel out. Yeah, this just equals 0. Like that. So if it's 0, square both sides, we're going to get a 2 minus z is equal to plus or minus, well, square root of 0, it's all just going to be 0. And then, so we solve for z. Just move it over to the other side, so z is equal to 2. Like that. So z is equal to 2. So this means, thus, well, actually, before we even get to that, we'll put the y. And then the y is going to be y is equal to 2 minus z. So 2 minus z is equal to 2 minus 2 equals 0. Yeah, so thus what we have is, thus 2 more points. 2 more points. And these are of intersection, so we're going to have 1. So when we have, when x is 1, when x is 1, we're going to have z is 2 and y is 0. So it doesn't change anything. So it's always going to be 0 and 2. And likewise, yeah, 2 more points. This or, I'll put, or and. So instead of or, put and then the next one is going to be, well, when x is -1, it doesn't change the z or y values, so it's still going to be 0 and 2, like that. Alright, so now we have 4 points, and we're going to graph these out, and we're going to get the ellipse. These are the points of intersection, so let's just graph these out now. So this is going to be, I'll make it not so big. Okay, this is going to be our y. This is going to be our x. This is going to be our z. And now what we have is, let's just put some points here. So alright, let's do the first one. Let's just put this 1, 0, 2. So this point here at 1, so we go x1, and 0 is stays stationary, then we go up to 1, 2. So in other words, it becomes this part right here. So this is a point right here. This one is going to be our point 1, 0, 2, like that. And that's this one right here. Now the next point is going to be at -1. So we go backwards 1. -1. Like here. Yeah, so that's -1. And then we go up 0. Doesn't... Oh, that's the y. That's the y. Whoops. Yeah, so it goes like this. This is on this side, -1. And then we go up, we go to the right 0, and then go up twice. It's going to be 1, 2. So it's going to be another point right here. This is going to be at -1 and 0 and 2. Like that. So it's on the same plane. So it's a bit nicer, like that, in 3D. Alright, that's that point. And now the next one is going to be at, right here, 0, 1, 1. So at 0, and then we go 1 here, and then 1 here on top. It's going to be somewhere around here. Alright, so that's going to be our 0, 1, 1. Yeah, I'll put this like this. This is our... Put the arrow like that. This is a 0, 1, 1. Alright, and it goes like this, and this is going to be a shape like this. It's be an ellipse. We'll draw it better later. But anyways, we have a point there, and then one more point. 0, -1, and 3. So it's 0, then it goes -1 over up here. -1, and then it goes 3 up top. So all the way here. So it's going to be somewhere around here. So again, try to visualize that in 3D. It looks something like that. It is a horrible drawing. But you get the idea, and it's going to be actually on points of this intersection across like that. Alright, so that's that. Alright, yeah, so that was a pretty bad drawing, but here's a better illustration from my calculus book. Alright, so here is a better illustration. There is the plane, there's the plane y plus z equals to 2. So basically a line like this, and the x direction goes infinite back and forth. That's pretty much, think of it as a line from in the z plane, and then the in the zy plane, and the x one goes to infinity. And this one here, x squared plus y squared equals 1, is just a circle with an infinite vertical component. The z goes to infinity, up and down. So that's that. And then if you see the plane of intersection goes to here, and there's the points 0, -1, 3, -1, 0, 2, 0, 1, 1, 1, 0, 2, and exactly what we had here in this one. I'm going to put stuff like here. This is going to be our -1, 0, -1, and then 3. Yeah, I think that's what we have. Yeah, 0, 0, 1, and 0, -1, and 3. So 0, -1, and 3. And again, this is a bit smaller the scale. This one is better shape there. All right, and again, I include the screenshot from my calculus book because I understand my own limitations. There's a drawing. There's a better one. Anyways, the projection of C onto the xy plane is a circle is a circle x squared plus y squared equals 1, z equals 0. So now we're going to look at this projection right here. If we take this the projection of C, so this is our C. This is our C. If you project it all the way straight down, what you end up having is actually a circle. You're going to have a circle like that. And that's just going to be the circle y squared, x squared plus y squared equals 1, and then z is equal to 0. So just set it to 0. So we know from my earlier video that we could write, and we could write it like this. So if we have a circle, so it's just a circle, if this is the y, and this is the x, and then we also know this is also the x squared plus y squared equals 1. Y squared equals to 1. And this is because this equals to, also for completeness, because this is a different example. So that's our x, y. We also know that x squared plus y squared equals to cosine squared t plus sine squared t equals to 1. And again, that's just the parameter. Yeah, this is the Pythagorean identity. So that means, and we also, basically means that we could write this in parametric equations using sine and cosine, and that's just an equation of a circle. And where when you have t equals to 0, plug into cosine of 0 is 1, sine of 0 is 0, so we have 1, 0 as a starting point. And then it loops all the way around in a circle, like that. So that is what we have. And yeah, so we know from my earlier video that we can write, so we could basically write these in the components. We can write these as parametric equations. So we have this, so we can write this the x component is just going to equal to cosine of t. The y is equal to the sine of t. Sine of t. And this is all for 0. T is between 0 and 2 pi, because it just goes, after that, it just follows back in the same circle. So from t is between 0 and 2 pi, we have a circle. We don't have to do loop that many times, just one time. So, because all we need to know is one loop. We're just asked to find the shape here for one intersection, not infinite in loops. All right. So from the equation of the plane, we know the equation of the plane right here is just y plus z equals to 2. So we have y plus z equals to 2. Yeah. So then, for parametric equations in 3D, our z, rearrange that, is just going to equal to, move this 2 on the other side, move the z on the other side, and so on. We're going to get z is equal to, z is equal to y minus 2, and then replace, actually, and not z as y equals 2. We'll move the y on the other side, so we have positive z. So we're going to have a 2 minus y, and y is equal to sine t. So this equals to 2 minus sine t, like that. Yeah, and since we're asked to find the parametric equations of this, so right here, come back here, so find a vector that represents the curve of intersection. It doesn't specifically say that find the parametric equation, but that's pretty much what we can do. So we could write parametric equations for C, the intersection curve, as, right here, we could write this as x equals, now it's in full 3D, x equals to cosine t, y equals to sine t. So now we have a 2D circle. And now we're going to have a 3D slanted ellipse right here. It's going to be z is equal to 2 minus sine of t, where t is between 2 pi, or 360 degrees, and 0, like that. So that is our setup there. And now the corresponding vector equation is, so we could write it in this format. So r of t, we could write this as, just write this in the basic. We could either write this as, I'm going to write this in both formats. So cosine t like that in the triangle brackets, sine t, and then 2 minus sine t, like that. Or the other one is just the cosine, so the McCuckle's book has it, cosine I plus sine t j, and then plus 2 minus t, 2 minus sine t. Sine t, and then this is k, and this is again for, all this is for 0 is less than or equal to t less than or equal to 2 pi. So that's the range. All right, and now this equation, or whichever one you want to use, this equation is called a parameterization of the curve C. All right, that's my pronunciation. The arrows in the earlier figure, or figures, I'm not sure if there's figures, I think it's just figure. Yeah, I didn't put the arrow over there. So in the earlier figure right here, see these arrows going down, and it's going up like that, and so on. So it's going in a circle this way, counterclockwise. And yeah, those ones, the arrows in the earlier figure indicate the direction in which C is traced as a parameter t increases, and we could see that from ours. So, and this one goes up like that because, well, it's based on the parameter t, not the x. Because right now we have x is equal to 1, negative 1, there's a 0, so we don't know where it's starting from, but when we start from t, so let's go from t equals to 0, what we end up having is, we're going to get, so when you plug in t equals 0, we're going to get a cosine t is 1, and then sine of t is 0, and then 2 minus sine of t is 2, like that. Yeah, so that is that. So in other words, the starting point is this right here. So that's the starting point. And again, there's our x, and think of it as the this is the at 1 0 at the bottom there. So this is 1. So, and it goes around like that. So basically, think of it the angle goes like that. From t is or the theta. So if you look at it as theta, yeah, t is in this case the angle, and starts at x equals to 1. And that's the same thing right here. So it starts off here. I'll just draw it anyways, like that. And this is our t. And actually, instead of that, I'll just do it like this. This is I'll just draw the full thing like that. So that's our t, like that. T goes around in a circle like that, and so on. So then this is the first point. So it starts off right here. Yeah, so that's the first point, and then the next one, and so on. And then the next one, we'll solve it right now. So the next one is, let's go at t equals 2 pi over 2. That's 90 degrees. So if you think about it this way, if you go at t equals pi over 2, that's at 0, 1. So this is at 0, 1. And that's because, well, when you plug this in, so at pi over 2, cosine of pi over 2, that becomes 0 now. That's just the cosine of 90 degrees. That's a 0. And then sine, that becomes at the maximum 1. And then 2 minus 1, that's just going to be 1. Yeah. So in other words, this is the next point. And then you obviously see, so it goes from here all the way down here, and it's going to go back up. And so that's set up there. And I'm just going to erase this as well. Or what I can do is, this is t. Like that. T goes from there. All right.